it would be, I would get 1 0 followed with all zeros. So if I perform ANDing of the mask with the destination address with prefix as 26 bits, I will get the last byte as 1 followed with all zeros. How much is this in decimal? How much would this turn out to be in decimal? It would turn out as 128, correct? So now if you look at the previous table, if I just show you the table for this, you see here, this 180.70.65.128, I got that value for the first row. Is it matching with the address entered in the first row? The network address in the first row is .192 when I have a 26-bit mask. If you have a 26-bit prefix or mask and you're finding the network address for the given packet's destination, you're getting 128 instead of 192. So the first row is not matching. So now what should I do? I should try to match it with the second row. Is it matching with the second row? Yes. If I, now I should use what is the length of the prefix. The prefix length is 25 bits. In the sense I should AND it with a mask which has 25 leftmost bits as 1. The mask value is 25 leftmost bits are 1. So when we do this, what happens? You will get the same address again. So if you take that value, if I take this value .140, I am taking the last byte. That .140 was represented as 100, then 0, I think 1100, something like this we had, right? Anyway, whatever it was, if I AND it with a mask which has ones in these 24-bit positions plus a single 1, I'll get 1 in this position and zeros elsewhere. Remember, all these are zeros. So you get 1 followed with 7 zeros and the value turns out to be 128 if I convert it back to decimal. Which means to say, now the address which I am getting for a destination address of 140, I am getting the network address as 128. Is it matching with the second row network address? Yes. Here I have an address entry as .128 and what you are getting through calculation is also matching with the same address. So once this match is happened, this router knows it will forward the packet through interface M0. It will send this packet on this interface and it knows that it can reach the destination device having the last byte address as 140. So if there is a device having the last byte as 140, it will be on this network, not on this network. Is that clear? Is this concept clear or do you have any doubts? So you have to explain the process of how individual router forwards it after comparing with this. That's what is explained here. So the first mask is applied on the destination and you get the result as .128. It doesn't match the first row. So now the second mask is applied on the destination, which is /25. Then again the result is excuse me. Again the result is .128, which matches with the second row entry. So it will extract that and it knows that it should forward the received packet on interface M0 to reach this network. Is that clear? This is how forwarding happens in a router. Next, let's see a concept known as address aggregation. So what is this address aggregation? Usually in classful addressing, there would be just, I was telling you this problem, one entry in the forwarding table for every large organization. The whole organization is represented with 1. Whereas in classless, what happens? There are multiple large and small organizations groups. So one would be large, one would be very small. There are multiple organizational groups, and for each one there would be one row in the forwarding table. So every organization has one row entered in the forwarding table, and if you have to do a matching, so using our regular technique, if a matching should be done, there are too many entries and it would take a very long time. Remember, every packet should spend very little time at every router. Otherwise, it will add on to delay. Say you send something now, you want the receiver to receive within a fraction of a second. Yes or no? We don't want every router to delay that. So if you want the receiver to receive it very fast, the router should do this matching and all that very fast. It should be very, very fast. And that would be difficult if I have too many entries in every router's forwarding table. So remember, for a network as large as the internet, if it should have so many entries, there will be few billion and millions of entries in every router. That is totally impossible, right? You can't imagine every router having billions of entries in the table. Imagine the amount of memory needed. Imagine how much time it will take to search. So what is normally done is they do something called as address aggregation. You'll understand this clearly in this example. You see, there are 4 organizations which are allocated continuous addresses. They can be 4 different organizations, but each of these organizations is allocated a set of addresses. Say, for example, organization 1 is allocated addresses 140.24.7.0 to how much? What is the prefix length? 26-bit prefix means the host ID will be 6 bits. 2 to the power of 6 devices. How much is that? 2 power 6 is 64. So what is the last address in this? 140.24.7.63 will be the last address. Is that clear? The last address in this first organization will be .7.63. So 64 addresses are given to organization 1. Similarly, the organization 2 starts with address 64, which is contiguous. It's the immediate next address with which organization 1 ended. From here, another 64 addresses, because this also has prefix length as 26 bits. So since the prefix length is 26 bits, another 64 addresses are given to organization 2. So its last address will be .127. Next, from the next address .128, organization 3 is given addresses, same prefix length. So another 64 addresses, .191 would be the last address. Finally, organization 4 will start with address .192 and end with .255. So 256 addresses are divided among 4 organizations, each a small organization getting only 64 addresses. So these organizations are small, for them 64 addresses are sufficient, and that's how they got that division. So the internet service provider would have given continuous addresses like this. Now what this internet service provider will do, he will use one router connecting all these 4 organizations to different interfaces in this router R1. And the 5th interface is connected to a second router on the internet. And what he does, what this internet service provider does, for router R2, reaching router R1 means he can access any of these 256 addresses. He can reach, if a packet which is there at R2 has to reach organization 3, its immediate next hop is R1. So it will identify all these 4 organizations clubbed together as one. So you can just look at the entry here. Can you look at the entry in this forwarding table for R2. R2 has a very small forwarding table. It will aggregate all this, the addresses from 140.24.7.0 to 140.24.7.255. In the sense, 256 addresses are aggregated into one single address entry. He just says 140.24.7.0/24. Look at the mask length. Actually, for each of these, if I have to identify one among 64, the prefix length is 26 bits. But if I take all the 256, 64 plus 64 plus 64 plus 64 as continuous and consider this whole thing as one block. So if I consider this whole thing as one large block, then what would be the address for me to reach? It would be 140.24.7.0, and this last byte can vary from 0 to 255. So I can access all 256 addresses. So what I'll do, I'll reduce my prefix length to just 24 bits because I can reach organization 1, 2, 3 or 4 with this single address. So that's what this router R2 does. It will consider the aggregated or grouped addresses together as one entry. It's easy now to make the entry. So are you understanding how we are overcoming the problem of long entries or large number of entries? You aggregate continuous addresses even if they belong to different organizations as long as they are accessed through a single router. So all these 4 organizations which are accessed through single router R1 can have an aggregated set of address like this: 140.24.7.0/24, and what? It can have a single entry at this router R2 telling anything which should reach one of these 256 addresses should be forwarded to router R1 via which interface of R2? M0. The interface M0 of R2 is connected to M4 of R1. So it will mention what is the outgoing interface. If I should reach 140.24.7.0, I should send the packet out on interface M0. So I have to forward this packet out like this. Then it will automatically reach this router. Once it comes to router R1, what should it do? It should identify to which organization the given packet should go. So here it should have a longer routing table entry. The forwarding table entry at R1, you can see how it is. So at R1, all the prefixes are of same length /26. So we'll begin with the first, the lowest address. 140.24.7.0/26 is my first entry. Again, if a packet should reach from R1 to this, it's a direct hop via where? Via interface M0. From R1, if I have to reach any device in this network, I should just send it out on M0. That's what we are doing. And next, if it should be sent to one of these addresses from .64 to .127, if I should forward it to one of these address, I should send it out on interface M1. So the second entry is this address 7.64/26 and the interface number M1. The third one will be this address, organization 3, interface M2. The fourth one will be this one, .192/26 and via interface M3. Now, please remember there should be a default. If the packet which arrived did not belong to any of these 4 organizations, its destination did not match with any of these, it should go, when we don't know what is the next address, you can simply enter this address. Do you remember this host address? 0.0.0.0. So you don't know what is the address of your next hop, just enter it, the default address 0.0.0. So that is considered as the next step. It can be address of its default router. If it doesn't belong to any of these, it should send it out to R2. Simple. It will send it to R2, where I'll put the address of R2 here, and on which interface will it send? On interface M4. So R1 has this forwarding table, whereas R2 has a smaller forwarding table. So this concept of address aggregation is very useful on the internet when we are connecting multiple when we are connecting multiple devices. It's very there are long paths, multiple routers. If you aggregate all nearby addresses into one large block, this would be very useful. Okay, so I think I'll stop with this for today. We'll continue in the next class. Maybe I'll be finishing this module. Okay, tomorrow let's try to complete this module. If you have any doubts, you can please ask.